Hello everybody, let us now continue our discussion on anion binding. So today we will be discussing about the factors that govern anion binding. We have already looked at in detail the factors that control binding of cations with different hosts, and what we realize is that the concept of pre-organization, which we will again revise now. So, the concept of pre-organization was found to be extremely important when it came to binding of cations with different hosts. Number 2 was the electrostatic complementarity, which was the next important factor, and the third important factor was the solvation dynamics. That means you have got both the solvation of the guest as well as the host, and it is necessary to desolvate the cation before it can effectively complex with the host to form the host gas complex. So, pre-organization, electrostatic complementarity and solvation dynamics were very important to the binding of cations with a suitable host. Now, when it comes to anions, the discovery of anions, as guests, this work can be traced back to 1968 when H.E. Simmons and C.H. Park actually started looking at anion binding in a series of molecules which are called kapatinands. So, let us look at how these kapatinands look like. So, these are my kapatinands, where we have got the bridge head nitrogens. These are the bridge head atoms, and these are protonated. So, first of all, it is preferable to have cationic host or neutral host which have the electrostatic complementarity to bind anions, and here n can be equal to 0, 1 and 2. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So, if n is equal to 0, then the number of bridgehead atoms is 8. If n equal to 1, number of bridgehead atoms is equal to 9. If n is equal to 2, then the number of bridgehead atoms is equal to 10. And number 2, we need large sized host, keeping in mind that generally anion size is greater than cations. So, these two features have to be kept in mind when we are going to design suitable hosts which are going to function in a complementary manner with the anions which are going to be the guest molecules. So, to start with, we know that the anions, So there are some important things we need to keep in mind before we consider anion binding, and anion binding is going to be more challenging compared to that of cation binding, because the anions are relatively large in size, and also they can come in different shapes and sizes. In case of cations, we preferably had spherical shaped cations. That means we had a positive ion, that is either divalent or monovalent or trivalent cation. But in case of anions, we are going to have different shape and sizes, and the charge density distribution is going to be different, and therefore the nature, this will affect or influence the nature of binding of the anion with the different cationic host. The second thing we have to keep in mind is that when you have a cationic host, you also have the counterion associated with the cationic host. So now you have two different anions, one associated with the cationic host and the other the anion of interest, which has to preferably bind with the cationic host. So there is now going to be a competition between these two ions, and so essentially what the binding constant indicates is the preference of one anion over the counterion, which influences the binding processes with the cationic host. So these are some of the challenges which anions will face, and the second important problem when we have anions is that anions have got strong solvation. So there is a high solvation energy associated when you put an anion in aqueous solution or in a particular solvent. So these solvent molecules have to be removed before the anion is free to effectively get encapsulated by the neutral or cationic host. The third important thing is that, which a very important factor, is the pH of the solution. The pH of the solution plays a very important role. Why? Because the operating pH in which the experiment is going to be performed, the anion should exist in that pH, and also the host has to be protonated. Either it should be partly protonated, or we can have a neutral host to start with, or we have partly protonated host, or we have a completely protonated host which is of a cationic nature. So the pH at which the host exists may not necessarily be the pH at which the anion will exist, because at low pH the anion will get protonated and form the neutral species. So there is also a competition of pH here, and that's a very important factor when we want to study anion binding kinetics or anion binding thermodynamics with neutral or cationic host. And keeping these things in mind, let us write down. So the important factors of consideration are: so I told you the important factors of, so number one, anions come in different shapes and sizes. For example, we can have spherical, chloride, bromide, iodide, fluoride. We can have the linear, SCN minus, the linear azide. We can have the trigonal planar, carbonate, nitrite. We can have the square planar, PTCl4 2 minus, or we can have PTCN4 2 minus. We can have the tetrahedral anions, for example sulfate, phosphate, etc. We can also have perchlorate, perbromate, iodate. We can have octahedral anions like PF6 minus or FeCN6 3 minus. And we can also have biologically relevant phosphates, for example P2O7 4 minus, and also the oligomers of these phosphate ions which are biologically relevant in nature as well. So we can have all kinds of anions of complex shapes and sizes, and all these anions would like to have suitable host which can effectively encapsulate these anions and form a supramolecular host guest complex. The second factor we need to keep in mind is the anions have higher degrees of solvation, and hence energy must be spent for the process of desolvation. For example, we can take the delta G hydration from potassium ion is around 300 kilojoule per mole, but it is minus 465 kilojoule per mole for fluoride. This is because of the higher charge density. That means the amount of electrons per unit volume. That means the charge density is much more higher for fluoride, because fluoride is a small anion and therefore the charge density residing on the surface is more compared to that of a potassium cation. So it is associated with such high magnitude of solvation, and this magnitude of solvation energy drops to minus 340 for chloride to minus 315 kilojoule per mole for the large size cation, that is bromide. The third important thing is that the anions stay deprotonated only in a small range of pH, and the receptors or the host molecules might not be completely protonated in this pH range in which the anion exists in the desired form. Okay, so this is something which has to be kept in mind. And the fourth most important point is that the anions are coordinatively saturated. Okay, that means we looked that they have the necessary coordination around themselves. So they are coordinatively saturated, and they bind by weak interactions like hydrogen bonds plus van der Waals interactions. So it is of interest to enhance the binding of anions with the cationic host via employing, for example, stronger hydrogen bonds and a stronger interaction, so that the binding is much more efficient. And also, to start with, let us take an example of binding of an anion. Now, binding of an anion, unlike that of a cation, does involve conformational change. For example, the kapatinands are not pre-organized host. Okay. So, then there is a change in conformation of the capatinand when it binds with the chloride ion. So, let us look at this conformational change. So, to start with, this is the conformation we have. This is the anion, this is the anion, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So, when we have this 8, 8, 8, so when this is 1, 2, 3, 4, 5, 6, 7, 8, 9, but when we have the 8, 8, 8, there is no binding. So, now we will see that this is followed by so 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the third one. So, you can see this is out conformation. This is the NH is outside, but now this is the in conformation. So, there is a change in the conformation of the capatinand, where the anions were initially present surrounding the cationic host, but now they are pulled into the cavity. Now they are pulled into this particular cavity where the anion is stabilized by N plus H Cl minus hydrogen bonds. These are the charge assisted. So, when you have this kind of hydrogen bonds, then there is stabilization which takes place. So, what was now proposed is that we need to now design the anions and cations which are complementary to these anions. So, the chemical design in anions host binding is very important. So, number 1 is the negative charge on the anion. So, to start with, we know that because electrostatics play a role and electrostatics are non-directional in nature. Therefore, if you have got say different anions present in solution, then both the anions, say you have got two different anions, then all the anions of both the types will be attracted towards the host, because the anions are non-directional in nature, the interactions are electrostatic which are non-directional in nature, and therefore, there will be no selectivity observed to start with if you have got a mixture of anions, particularly of the same shape and size. For example, if you have chloride or bromide or iodide, then the chances are that all these anions will be attracted towards the host simultaneously. But what has been observed in case of capatinand, that when you have the 888 capatinand, I wanted to give you the data, then there is no binding, but when you have the 999 capatinand, then you have, this is the binding constant for chloride, and when you have the 10-10-10 which is a larger sized host, then it binds chloride, bromide and iodide, but no selectivity. So, this is the problem. Now, you have got a much larger sized host which has got a bigger void, and if you have different anions which are present in solution, for example chloride, bromide and iodide, then it will be able to bind chloride, bromide and iodide with equal efficiency, and therefore there will be no selectivity which will be observed. Because to start with, the anions have got a negative charge, they are spherical, and they are attracted by with the cation by electrostatics, and electrostatics are non-directional in nature, and therefore we have to see that in order to have selectivity, you will have to actually play with the solvation processes or the cationic host, so that you can have preferential binding. So this is a challenge with anions. Number 2 is that whether we can look at the Lewis basicity. Whether we can look at the concept of Lewis basicity. Now, vast majority of anions we know are Lewis bases, and because they have got lone pairs of electrons. Okay, and so what we can have now is that we can have hosts that have Lewis acidic sites. For example, boron or mercury or tin, which can now coordinate with the Lewis basic sites and form host guest complexes. And these kind of interactions are called anti-crown interactions. These are called anti-crown interactions. So, what we can now see, for example, is that we can have this kind of a host when mercury is the Lewis acid, and we can add bromide anion, and it has been observed that the bromide now interacts with the mercury atom, and it sits in a Pershing geometry, and the equilibrium distances between mercury and bromide ion is 3.1 angstrom. A true covalent bond between mercury and bromine is 2.54 angstrom. So, these kind of non-covalent association takes place, and these are referred to as anti-crown interactions, where you have a Lewis acidic site in your host, and that can interact with the Lewis basic sites, for example anions, and form these kind of host guest species. The nature of binding of the anion actually depends upon another very important factor, that is the contact surface area. Because these are having electrostatics as the primary driving force. Therefore, once the anions comes in the vicinity of the host, then it would like to maximize its contact with the host, and therefore the surrounding surface area becomes very important, and also one should be able to polarize the electron density of the anion to effectively complex the anion with the host. So, the polarizability of the anion is important, because we are looking at weak interactions of the van der Waals type. So, and van der Waals interaction essentially depend upon the fluctuating electron density, and when the atoms come close to each other, that it is the anion. If we can polarize the electron density associated with these anions, and they will contribute to enhanced binding. Therefore, greater area of contact between anion and host leads to enhanced binding. And the fourth important factor which has to be kept in mind when you design a suitable host for anion binding is the solvation. So, the anions are strongly solvated by the solvents and solution anion complexation measurements the solution anion complexation measurements will influence the magnitude of the binding constants in which these are carried out. Okay. So, anions are strongly solvated by the solvents, and hence solution anion complexation measurements will influence the magnitude of the binding constant in which these are carried out. So, for example, the binding constant is approximately 10 to the power 2 to 10 to the power 3 in water for the halides, and it can also be done in different solvents where the magnitude of the binding constant is more in DMSO, more in acetonitrile, more in chloroform, and more in CCl4. So, this is the order of the binding constant for a set of halides in different solvents. So, this kind of complexation behavior is of relevance, which is influenced by the solvents, and the magnitude of the binding constant increases when you change the solvent from DMSO to MECN to chloroform to CCl4. Now, let us look at one example to further understand the role of pH, which is extremely important here. A simple change in pH, this is the next important factor. So, we looked at all these factors, negative charge, basicity, polarizability, solvation. We also looked at the pH here, that is, we looked at the important factors of consideration. So, now let us look at what is the role of pH here. So, for this we will again go back to our old example where we looked at the soccer ball complex. The soccer ball complex where we had the soccer ball complex, and we can again draw these so we have 1 2 3 4 5 and then we have here another one I am drawing. Now, we can first consider the neutral complex, that we have seen that it is a very good receptor for the ammonium ion. We have studied this when we studied the binding of the soccer ball with organic cations. That means, we looked at So, we looked at the ammonium binding here, and this was towards us, this is behind, and then these two are in the plane. Now, if we now change the pH of the solution, that is we now go to partially protonated host. These are the partially protonated host, then we will see that they will function as good, good host for water molecules. So, we can see here, so we see this is the water molecule. So, it forms OH N hydrogen bond and N plus H O hydrogen bond. So, there are two of these type and two of this type, which stabilize the solvent molecule, that is water. And if you actually want to now consider an anion, then we will have all four of them protonated, and then we can have the chloride sitting here, and this form the N plus H Cl minus charge assisted hydrogen bonds. So, as you increase the pH of the as you change the pH of the solution, that is, if you make it more and more acidic, that means you are lowering the pH more and more acidic, you are lowering the pH of the solution, then the active species of the, that is the host, which is the species, active host species changes, and depending upon the pH, it can function either as a good host for ammonium ion, for water molecules partially protonated, and this is fully protonated, it can be a very good host for your chloride anion. So, this is these are called tetrahedral receptors, and in this case of tetrahedral receptors, they have got very good affinity for these ammonium, water or chloride ion, depending upon the pH of the solution. And it has also been observed that the log K value when measured in methanol and water is equal to 4, okay, is equal to 4, and the selectivity factor for chloride over bromide is 50. That means, now you can see here that we bring in the concept of selectivity. So, initially we were saying when you have different kind of anions, for the kapatinands, chloride, bromide and iodide were not very selective, they were all undergoing encapsulation by the kapatinand. But now here we can see that the host has been designed in such a way that there is a greater affinity and selectivity for chloride over bromide. And what we have seen here is that the optimal distances are 3.09 angstrom between hydrogen and chloride, and these correspond to the fact that the host now is also more pre-organized, there are more electrostatic interactions, there are greater binding sites, and all this promote enhanced binding. So, we now have a more pre-organized host. Number 1, greater positive charge on the host, greater number of binding sites, and all these are responsible for enhanced binding of the anion. In the case of the bromide, the binding is not very strong because it forms longer NH-Br distances, and therefore this is not an optimal match for the cavity size, and therefore the extent of binding is weaker, and hence extent of binding is weaker, resulting in lower selectivity. So the cavity dimensions here are more appropriate for chloride, whereas the distance are much more longer for bromide, and therefore this is not an optimal match based on the cavity size which is created, and hence the extent of binding is weaker, and hence resulting in poor selectivity of bromide compared to that of chloride. So with this in mind, we will now close this lecture, and in the next lecture we will look at the other factors which influence the processes of anion binding. Thank you.